Hi, just wanted to discuss one way of reducing common mode noise when making measurements with an oscilloscope. This is just one method which I happen to use. It's not necessarily the best method and it's not always appropriate. The oscilloscope is set for AC, 1 megahertz, just normal termination there. Again, that's not always ideal, but it is safe. You're unlikely to damage the oscilloscope if it's set there. And what I've got is I've just got a spectrum view here, and you can see here some measurements. So there's 80 microvolts of AC RMS noise and about 700 microvolts peak to peak. That's with nothing connected to the oscilloscope at the moment. And I've got no averaging or high res mode or anything like that configured. So yeah, just basic oscilloscope settings there. For the device under test, I've got a power supply, but it's going to be unpowered, and I'm just going to be testing the noise with nothing powered up there. And what I'm going to use is BNC cable, and this is a brand new one, a Tektronix one. So I'm going to just open that up and connect that. At the power supply end, I'm going to use this, so banana plugs to BNC. And this is not ideal. I didn't make this specifically for this test, and the wires are a bit long, but I am twisting them just to try and reduce some of the noise pickup. So here is connected up. I've just shorted them there, and it's then connected to that new cable, that BNC cable. And now if you have a look, you can see that the AC RMS noise is quite high. It's 700-ish microvolts RMS, and the peak to peak is very high. It's about, well, it's more than 30 millivolts, and that's even with the power supply switched off. So that is really coming from common mode noise. So using that cable and just attaching it like that has caused that noise to be visible, as mentioned. So yeah, it's that's in the 30s, and it can go even higher. That peak to peak value in millivolts. One option is to add on these ferrite clamp things. So you just clamp them over, but often it doesn't make that much difference. I don't know if you can tell, but that's gone down a tiny bit around there, around 20 megahertz, but the rest of it kind of looks unaffected. And that's because some of these ferrite cores are more useful for some frequency ranges than others. And also, one ferrite core often isn't enough. You might want to pass the cable several times through it, and you might want more than one ferrite core, especially different cores for different parts of the frequency spectrum. But this gets difficult to do with thick coax cable, and you do want decent coax as well, ideally double shielded. So yeah, it's tricky to do with these. If you're not too concerned about bandwidth, for example, if you're not measuring to a particular standard, you just want to get a general idea of what's going on, you could just use screened twisted pair cable. So this is actually microphone cable, which happens to be star quad cable, and it has got a double shield, as I understand. I have to check that. It's been a while since I made this cable up. And you can see I put a ferrite here, and then just soldered the two ends, the star quad cable into just a BNC plug there. But I've also got another ferrite here, looped several times through there, and then yet another one with 3 passes in there, and then the other end there's one more, and then I've just shorted that. So let's try this one. So that's connected up exactly as described, and you can see now that the peak to peak value is probably a tenth of what it was, and you can see there it's had quite a significant impact. This does go to show just how difficult it is to make low noise measurements, and like I mentioned, this is not necessarily the best way to do it, but it's a fairly safe way, just using the AC 1 mega ohm setting on the oscilloscope. Okay, and using that cable, I've now turned on the power supply, so that's going to be my device under test just for this simple experiment. It's set to 5 volts and the output's switched on, and you can see now that the values there are 5 or 6 millivolts peak to peak and 200 microvolts RMS. So that peak to peak value and the RMS value, there is some contribution there from the cabling which I'm using, but nevertheless that's pretty low noise. Regarding how much impact the ferrites had on the measurements, initially there were just these two ferrites attached, and that got the noise down from that 30 millivolts peak to peak down to, I think, maybe 10 millivolts peak to peak. I can't remember entirely now. And then adding on this one got it down to about 7 millivolts peak to peak. And then adding this huge thing. This is a Type 43 ferrite, by the way. That, and then reduced it down to the current 3 millivolts peak to peak that you're seeing. Ideally, if you want to preserve a bit more bandwidth, you'll want to put a series termination resistor at the power supply end. The output impedance of the power supply is going to be very low. So if you're using coax cable, then 50 ohm series resistor, which could be two 100 ohm resistors in parallel, could be inserted in there. I'm actually using a microphone cable again, but it's tightly twisted, and I'm guessing the impedance is between 50 and 100 ohms. So I inserted two parallel 100 ohm resistors in there as well and labelled it appropriately. With the power supply off and the inputs just shorted, and that cable's just connected to the oscilloscope, I can see the noise is about 10 millivolts peak to peak. And that's with no ferrites at the moment. Now I've got 7 turns on the ferrite there, and the noise is about 1.5. About 2 millivolts peak to peak. I've added some more ferrites, and you can see it's not made much difference now. And you can see I've turned on the markers, and the main problem seems to be around 65 kilohertz, 63 to 65 kilohertz. There's some noise there which I've not been able to identify the source of. I couldn't resist one more test. I've now got 2 ferrites here because I figured maybe I can't do anything about that noise at 60 kilohertz, but maybe 2 of these could make an improvement. And I've got an improvement, but I also had to turn off some of the lighting. So that 60 kilohertz has actually disappeared. I turned off some of the lighting around the house. And now the peak-to-peak noise is about 1 millivolts, 80 microvolts RMS. I think that's definitely as good as I'll get it today. Thanks for watching.